Hello everyone, myself Dr. Vijaykumar, Associate Professor, Department of Electronics and Communication Engineering, Aditya University. In today's session, we are going to see the moments of random variable. So at the end of this particular session, we will be learning two learning outcomes. Learning outcome 1 is understanding the definition of moments of random variable and classifying different types of moments. And next to learning outcome is we will apply the concept of these moments for solving the real-time problems. So what is meant by moment? So moment is nothing but a quantitative measure related to the shape of the distribution of a random variable. Okay. So this will help us to describe the properties like location, spread, skewness, kurtosis of the probability distribution function. So if we want to measure the spread of the distribution function, so the thing is we use this variance. If you want to locate the central value, the statistical parameter is mean, and if you want to measure the symmetry, the skewness is the parameter which is used. So these parameters can be measured with the help of the moments. So moments describe the shape of the distribution function, and from the moments we will get a lot of information, and moments are generally classified into two categories. Moments about the origin, moments about the mean. So the fundamental operation is expectation for a random variable. So moments are the operations on a random variable. Okay. Moments are also the operations of random variable which can be related to expectation and variance. So moments about the origin is in general denoted as Mn. Moments about the mean, or this is also sometimes regarded as central moments. Moments about the mean is termed as mu n. The notation we follow is mu n. So where do we use these moments? There are a lot of applications where we will apply the concept of moments. So first, in the definition itself, we have seen moments describe the distribution characteristics. So they will give the information about the shape, characteristics, all those things, symmetry, and also they will be helpful in estimating the parameters, and also to fit the distributions to the data, and it is also used in hypothesis testing. So first one is moments about the origin. So already we have seen all these things, we are recalling for solving the problems. So moments about the origin is generally defined as expectation of x power n. We use concept of expectation here. Expectation of x, already we have seen expectation of x power n. Expectation of x power n is nothing but nth moment about the origin, where n is nothing but order, where n is nothing but order. So if n is equal to 0, 0th order, n is equal to 1, first order, n is equal to 2, second order, like that. So when n is equal to 0, expectation of x power 0 is expectation of 1. So expectation of 1 is 1. So expectation of constant is constant. Similarly, when n is equal to 1, expectation of x, this is nothing but mean. N is equal to 2, expectation of x square, which gives you the mean square value or average power of the signal. So we know that the random variables are classified into two types, continuous and discrete. For a continuous version, the formula we apply is with the help of density function. For a discrete version, we use the concept of probabilities, P of xi. Okay. So another moment is moments about the mean, central moments. So central moments are mathematically defined as mu n is equal to expectation of x minus x bar whole power n. Okay, where x bar is the mean, x is the instantaneous value, x minus x bar. For a continuous random variable, this is the formula. For a discrete version, this is the formula. So when n is equal to 0, so expectation of x minus x bar whole power 0. So expectation of 1 is 1. When n is equal to 1, expectation of x minus x bar. So expectation of x minus expectation of constant is constant. So that will be 0. When n is equal to 2, expectation of x minus x bar whole square. We know that this is mathematically equal to variance. So mu2 is also mathematically equal to variance. Next, mu3 is equal to expectation of x minus x bar whole cube. This is skew. Okay. So, each and every parameter, each and every one will describe the shape characteristics of distribution function. For example, the moments about the origin r is equal to 1, this is mathematically equal to expectation of x. We know that the expectation of x provides the data of measuring the central tendency. Central tendency or central value can be computed with the help of mean. It describes the central tendency of the data. Next, r is equal to 2. Here r is equal to 2. This is central moments. Central moments r is equal to 2 sigma x square is equal to expectation of x minus mu whole square. It gives the information measure of dispersion or deviation or spread. So, how much it is deviated from the central value can be computed using variance, and r is equal to 3. This is nothing but skewness, and it is mathematically defined like this, and it gives you the information about the measure of asymmetry. Measure of asymmetry. When skew is equal to 0, that is symmetrical. When skew is equal to some value, it is asymmetrical. And similarly, r is equal to 4, and this is called kurtosis. It gives you the measure of tendency or peakedness or tailedness in the curve. Measure of peakedness or tailedness in the distribution function or the given function. So, all these four parameters will describe the shape of the characteristics of distribution function, and there is a relationship between moments and central moments. So, they can be interrelated to each other. So, for example, let us take mu2 is equal to, we know that mu2 is expectation of x minus x bar whole square, which is variance. Variance is also can be written as expectation of x square minus x bar whole square. We know that E of x square is m2, x bar whole square is m1, m2 minus m1 square, mu2 is equal to m2 minus m1 square. So, this is the relationship between second central moment and first moment about the origin and second moment about the origin. And similar manner, we can also relate mu3. So, all these are done with the help of the formula. This is the formula we are using. Based on this formula, we can relate central and moments about the origin. This is based on the binomial expansion formula. We use this one for relating the central moments and moments about the origin. So, mu3 also can be related like this. Mu3 is equal to m3 minus 3 mu x sigma x square minus m1 cube. So, mu3 can be interrelated with the moments about the origin using this relation. So, let us see some problems related to moments. So, the problem is given that the exponential density function is given in the problem, and he is asking us to compute the variance and coefficient of skewness. We know that the variance is mathematically defined as mu2. Variance is nothing but mu2 sigma square. So, mu2 is interrelated with moments about the origin in the form of a relation mu2 is equal to m2 minus m1 square. So, firstly we need to compute m1. m1 means expectation of x or average value. So, first we will compute m1. m1 is equal to E of x, and this problem already we have seen. So, the expectation of x for a density function if exponential density function is a plus b. Next, we need to compute mean square value E of x square, that is m2, x square into fx of x dx. So, here we need to apply the rule u dv rule. So, that is uv minus integral v du. Applying that rule, we will get the mean square value as a square plus 2ab plus 2b square. We know that the variance is related with the moments about the origin as m2 minus m1 square. So, mu2 is equal to m2 is e of x square, m1 square means e of x whole square. So, e of x square is this one. Next, e of x whole square is a plus b whole square. So, a square plus 2ab plus 2b square minus a plus b whole square. Solving this, we will get b square. So, mu 2 or variance we will get b square. Okay. And another question is asked skew. They are asking us to compute the skew. So, we know that skew or coefficient of skewness is mu 3 by sigma x cube. So, first we need to compute the mu 3. So, for computing mu 3, we know that mu 3 is related with the moments as m3 minus 3 m1 mu 2 minus m1 cube. So, first we need to compute m3. m3 means e of x cube. E of x cube can be computed as x cube into fx of x dx. Again we need to apply the udv rule. After solving this, we will get the third moment about the origin as a cube plus 3a square b plus 6ab square plus 6b cube. So, mu 3 is equal to m3 minus 3m1 mu 2 minus m1 whole cube. So, m3 is this is and mu x is a plus b, variance is b square, again mu x is a plus b. So, solving this we will get mu 3 is equal to 2b cube. Next we need to compute the sigma x cube. Sigma x cube, we know that sigma x square is b square, that implies sigma x is equal to b. So, sigma x cube will be correspondingly equal to b cube. So, 2b cube by b cube. So, the coefficient of skewness is 2. So, what does it indicate whenever a coefficient of skewness is 2? So, it is a measure of asymmetry. So, here coefficient of skewness is 2, that means definitely the wave or the function will have some bit of asymmetry in the curve. Next one, for example, you take uniform density function. Uniform density function is symmetrical about the origin, symmetrical about the y-axis. You can see this is symmetrical about. For this one, if you compute the skewness should become 0 as per the definition of skewness. So, skewness is a measure of asymmetry. So, clearly this is a symmetrical thing. For a symmetrical thing, if you measure the asymmetry, it will be obviously equal to 0. Next, a random variable x has a density function fx of x is equal to k into x square minus 5x plus 8 over the limit 0 to 4. They are asking us to compute the different moments, moments about the origin and central moments m0, m1, m2 and mu2. We know that first before computing the moments, we need to compute the value of k. We know that area under any density function, if a density function is a valid density function, area under the valid density function must be mathematically equal to 1. Equating this, we can compute the value of k. So, here the same thing is done, substituted the limits, we will get k as 3 by 40. Now, we can conveniently compute m0, m1, m2, mu2. So, mn. So, instead of computing m0, m1, m2 in a different manner, here they are simplifying the task by simply computing mn. When n is equal to 0, you can compute m0. When n is equal to 1, you can compute m1. When n is equal to 2, you can compute m2. So, x power n fx of x dx, this x power n a power m into a power n is equal to a power m plus n, that formula is applied here and computed, and the final values are these things. Now, when n is equal to 0, substitute in place of n 0, we will get 1. When n is equal to 1, we will get the first moment about the origin. When n is equal to 2, we will get the second moment about the origin. So, once you know the moments about the origin, we can relate the central moment mu2 as m2 minus m1 square. So, m2 is 1.4.16 minus 1.6 whole square. So, solving this, we will get 1.6, variance as 1.6. So, like this we can use the relationship between central moments and moments about the mean in solving the problems. So, these relations play a very key role because it will simplify the calculation. So, when you remember something like mu2, mu3, you can greatly simplify your calculation when you know the relationship between central moment and moments about the origin. So, earlier problems we have seen the problems related to the continuous random variable. So, here we will see the problems related to the discrete random variable. For a discrete random variable, moment about the origin is given as mn is equal to summation xi power n p of xi, and similarly minus infinity to infinity x power n fx of x dx. This is for continuous random variable and this formula is for discrete random variable. Now, we will use this formula discrete random variable for computing all the statistical parameters. They are asking us to compute the first moment about the origin, that means m1. m1 is equal to summation xi p of xi. So, here xi means this one 0 into 0.1, 1 into 0.2, 2 into 0.4, 3 into 0.3. So, we will get 1.9. Okay. Next, here next we need to compute the second moment about the origin. Second moment about the origin means e of x square, that means summation xi square into p of xi. So, x we know 0 square into 0.1, 1 square into 0.2, 2 square into 0.4, 3 square into 0.3, like that. Add all these values, you will get the 4.5 value as mean square value, which is the average power. Okay. So, when you know the mean, square value, you can compute the variance because variance mu2 is equal to m2 minus m1 square. Variance is 4.5, mean is 1.9. This whole square we will get 0.89. Okay. Now, this problem is related to the continuous random variable. A continuous random variable is given. Now, we need to compute the first, second, third moments about the origin. So, pretty much direct formula mn is equal to minus infinity to infinity x power n fx of x dx. So, this using this formula we can compute. Okay. When n is equal to 1, first moment, when n is equal to 2, second moment, when n is equal to 3, third moment about the origin. So, first moment we got 2 by 3, second moment 1 by 2, third moment 2 by 5. So, m1, m2, m3. Okay. So, in this session what we have seen is we have defined the moments and also we classified the moments. So, what are the different classification, and also we have seen the relationship between the moments. So, using all these things we have solved few problems on moments. So, some real time problems which is related to discrete random variable as well as continuous random variable. So, in the next session we will see the transformation of random variable, how to transform one random variable to another random variable. We will see some more real time problems on transformation of random variables. Thank you.